So you can't just plop theta into that expression because of the way it's defined up here. I'll show you how you can do that later. Okay, let's do the acceleration problem. So differentiating then this velocity one more time, differentiating this velocity expression one more time, then we get the acceleration of A is equal to the acceleration of B plus the acceleration of A relative to B. Now I hope you do enough of these kind of problems that this kind of formula is automatic to you. As I said, we get to later in the course, we start doing a lot of this. And so I want you to be comfortable at this level. So the acceleration of A, they told us,
was 3 meters per second.
was what?
3 meters per second.
Okay, so 3 meters per second squared, right? And this, you're rotating over here at a constant speed, angular speed. So the acceleration of A is simply 3I. The acceleration of B, the person in the Ferris wheel car going around at a constant rotational speed. Oh, very good. Okay. It's not 0, is it? No, because what's the path? The path is circular. If you're on a curved path, you've got acceleration, and if you're in motion. If you don't remember anything else in this course, remember that. Okay. So back here then, you can see that if we're in a constant, we have no angular, or excuse me, no tangential acceleration. No tangential acceleration, but we do have normal back towards the center of curvature. Let me go ahead and draw a little sketch here. Position. We have this normal acceleration of B, which we know is the velocity of B squared over R for circular motion. Right? Another way of writing that is what?
R theta dot squared.
R theta dot, or R omega squared. If we use the R omega squared and we point it, let's see, here's theta, right? Which means that this is theta, which means that if we took that theta reading the way it's defined here and added 180 to it, or pi, right? Then we would have that standard angle for this direction, wouldn't we? The standard angle for that direction. I want to do it that way with you for a reason. Do some trigonometry to just bring up your skill level if you've gotten rusty on it. Everybody agree?
Yeah.
I could write that as theta plus pi. Now our special case obviously is this is 45. Okay, so I want to write the acceleration of B now. So the acceleration of B is only the normal term because we know the tangential is 0. So the normal term then is going to be of the magnitude R omega squared. Our R is 9. Our omega was pi over 10. Right? That's the magnitude. That's the magnitude. And now the direction of it is cosine of this standard angle. Cosine of theta plus pi, comma, sine of theta plus pi. Plus the relative term. Excuse me? Think about, that's the reason I wanted to do this. You all agree that the x component should be negative. Matter of fact, the y component should be negative. what I'm pointing out to you, if you use a standard angle description of it, as I've done, then think of this, 45 plus 180, 225. Cosine of 225 is negative, right? Sine of 225 is similarly negative. So if you use standard angle notation, you can't screw it up. Well, it's very hard to. The x term is always going to be the cosine of the standard angle, and the plus or minus character is always built in. It'll always be built in. Similarly with the sine. Okay? So you might find that to be very handy. If I was going to generalize that velocity problem like we talked about a minute ago, I would have done it this way. Okay. So here's the math, and then we just drop in the goodies to solve that for that acceleration. So we collect the I terms, and so the I terms are made up of, leave the 3 over here, and we're going to subtract this term from it. So what I'm doing is I'm showing you the generalized form of it first. So 3 take away this 9 pi squared over 100 times this cosine term of theta plus pi. That is our I term. And then our j term is going to be this term with the sine brought over to the other side of the equation, becomes negative 9 pi squared over 100 times the sine of theta plus pi. And that's going to be j hat. At theta equals 45 degrees. Theta equals 45 degrees, or pi over 4, okay? Then we end up with 9 pi squared over 100, cosine of 200, imagine that's 45 degrees plus 180, 225, that becomes a negative square root of 2 over 2. I combined with this 3. So those terms become additive then, right? 3 plus this. And then the j term, again with 45 degrees in there and 180 degrees in there. That sine of 225 is also negative. So this will turn to be positive. 9 pi squared over 100, negative times the negative, square root of 2 over 2. J. Units, meters per second squared. If you punch that out, you should get the values they've shown in the book. 3.63. This looks like it. Sometimes I oftentimes eyeball these things to see if I'm in the ballpark, because it's easy to mispunch things with your calculator. And I'm seeing this is kind of like a 9 here, times 9 is 81. 81 over 100 is less than 1. And then this radical here, this is like radical 2 in the denominator. So you're getting something less, definitely less than 1. Okay?
3.63 was 6 days.
Okay, that's perfectly fine. I hat, and then eyeballing this similarly, it's only going to be that kind of a term, so that should be the 0.63. Okay. J hat meters per second squared. Now, the reason I decided to take the time to generalize this, everybody with me on the generalization standard angle technique? So let's say, I've got to fix my wires here. Let's say that we're at the bottom of the Ferris wheel. What should be the relative acceleration? Just think about it for a second. Just think about it without looking at the math. at the bottom of the Ferris wheel. So you're down, you're coming around, you're going through the bottom of the Ferris wheel. The relative acceleration, that car is scooting away from you that way at 3 meters per second squared, right? Moving away from you, 3 meters per second squared. And you on the Ferris wheel, your acceleration is which way here at the bottom? Upward. And so you should see this to be simply your normal acceleration value, J, and your 3I. With me? Those two components. Let's check it out. If you're at theta, let's see, what theta would give us the down position? Careful, it's defined this way. We're rotating that way. Negative 90. Negative 90 degrees. So let's see, do I have room on the board somewhere? Let me come over here. Ferris wheel, car. We're here. Acceleration should be this. Acceleration over here is 3, was it? Yep. And this thing should be the normal, which is 9 pi squared over 100, right? If we look at the math in the generalized condition using minus 90 degrees there, down at the bottom here for B, then this thing using this equation right here, cosine minus 90 plus 180 is what? Cosine 90. Cosine 90 is 0. That term disappears. Okay? So you end up with 3, sorry. That's our I component stuff. That, do I need to do that here? If we're at minus 90 degrees plus 180, that yields 90 degrees. Cosine of 90 degrees is 0. So you end up with 3I, here it is, and at minus 90 degrees over here, that's 90 degrees. The sine of 90, you know, is 1. Sine of 90 is 1, so you end up with this term, which is negative. Does that feel right to you? For the relative acceleration being negative? Does that feel okay to people? This is the this.
It's okay, because if you're going up, it looks like the car's going down.
That's the point, as Daniel said. Right? Okay, this is a relative acceleration, remember. You're the observer here. What are you sensing about watching that car over there? It appears to be accelerating away from you at 3 meters per second, because this thing doesn't have any horizontal acceleration at that instant. And even though you're accelerating upward here, that car appears to be accelerating downward relative to you. Okay. Right. So that pretty well covers the fundamentals here at this introductory level on this. Okay? Questions? Feel good? Okay. Let's take the rest of the time today to go ahead and get going on constrained motion. So the best way to probably start with this on constrained motion is to see an illustration in the book, and then we will go ahead and tackle some specific problems on that. There are a couple of ways of doing these usually, and I'm going to show you a page here. Okay. You need to determine, when you're doing constrained motion, you need to determine how many degrees of freedom exist. So we want to know the number of degrees of freedom. The easiest way to do that, if you have bodies hooked, one particle hooked to another, is for you to simply count the strands. Like if I look at the cable here, it's hooked onto A, and I can track it over the pulley and over this pulley and back up here. It's a single strand of cable. So that's treated as a 1 degree of freedom system. 1 degree of freedom system. Let me turn the page and illustrate something over here. If you look at this, you track a strand of cable like from body B, mass B, and you can follow that strand of cable to here. So there's one strand. And then grab a hold of the next cable and follow it around. So there are 2 strands of cable. This is a 2 degree of freedom system. So let's make sure we know how to find out the number of degrees of freedom. So the best way to do that is to go to problems and have you help me determine that.
Well, what degree of freedom means a variable that it depends on?
Well, we're going to have to write that number of equations to get the connection between the 2 bodies then. Okay, is what's going to be going on. So look at this problem right here. Right, notice this pulley right here. Some people, sometimes they ask questions about what's going on there. Well, this pulley's hooked to the roof, so it's pinned right here. And then the cable strand starts there and then comes on down. Okay? So how many degrees of freedom exist here?
1. You only have to know where one block is.
Just walk your way all the way around there, and it takes you all the way, and you can consider this to be where body B is located. Everybody see that? You can consider this position to be where body B is located. Okay? Because this is an unchanging length there. This length right here is unchanging.
So you just basically consider that body to be a fixed particle where it's attached
Right.
to whatever it's attached
Where it's attached to the pulley. Same thing over here. I would consider this the physical position of body A. Okay? And you'll see when we start doing some problems here how this works. Now let's look at this one, which we'll probably tackle a little later today if we get time. Whoops, I gave you the answer right up there. Sorry. It's hooked onto the roof up there where my pen is. Okay? Count the number of strands there. Everybody see it? How many? There are 3. 3 strands, so that's a 3 degree of freedom problem.
Not counting strands, but from counting the number of other blocks. I don't see the method of counting strands. That's just confusing. There's too many of them there.
Start here.
Okay.
Okay. Watch the pen. 1 strand up to the roof.
Okay.
Okay. Now come over to another piece of cable. Here's another piece of cable hooked on here. Track it. That's the second piece of cable. And then there's a third one hooked on here, right there.
Okay.
So we have 3 degrees of freedom. So don't count the number of blocks that are there, don't count the number of pulleys, count the number of separate strands. Okay, so what I'd like to do to get this problem going is let's look at one like, well, how about this one? Right here. Let's see if I can get this set so it'll show up nicely without falling off of here. There, that's pretty good. 1 degree of freedom. 1 degree of freedom. So we'll start working on it. So we have the fixed support at the top. Cable comes down, goes around a pulley, back up, through a support pulley at the top, and then wraps around that pulley, and heads down at an angle no angle given. Okay. Onto a ramp. And the block is hooked on there. And they describe the position of that right-hand block A as some distance x from some reference point. So here's the problem. Okay? So there are typically 2 approaches to tackling these problems. The approach that's emphasized in our book is probably the most convenient and easiest to use. What you do is you find a non-moving reference, such as up here at the top, and you try to write an expression that involves something that's variable. So I have this body B is down here, and it looks like it's effectively at a position distance down off of the support up here, that pulley, and it changes with time, doesn't it? So we could call that distance y sub b. Y sub b. Feel good?
Okay,
Julie?
So you're saying, oh, okay, nope, I'm good. Never mind.
Is that right? Okay. Now, you come over here, and it looks to me like, actually, you know what we could do? I think we could use this as our reference level, doesn't it? At this level right here. Does that make any difference if I call that my datum? Right here instead, this where that pulley is fixed, that level, and call that y sub b. Does it seem reasonable? Yeah. Okay. And then we can come over here and we can look at this, and we have some length of cable here. We could call that y sub a. Now, the way you do these problems, the most convenient way to do these problems is to write an expression that describes the length of this cable. This cable length is made up of, looks like 2 pieces that are y sub b long, right? Here and here, right? So 2 y sub b. Feel good? Plus y sub a I hate using this colored stuff because it doesn't come off the board very well. but I'm going to. There's some more stuff here, isn't there, on that cable? Doesn't this little piece here remain constant? Isn't that always there? And isn't that piece of cable right there constant, always there? And this piece up here, always there? Okay, so what we've got going on then is we've got this cable length made up of 2y sub b, y sub a, plus a portion of the length that remains constant. Now remember what we're doing. We're doing kinematics, the geometry of the motion. So we come up here and we crank the derivative on this. Derivative of a constant is 0. L dot is 0. We get 2y sub b dot plus y sub a dot and plus c dot. Its derivative is constant, or the derivative is 0. So we have a relationship between the velocities of this body in motion and that body in motion. I forgot to write down what the question's asking.
Determine the acceleration of B if the acceleration of A is given.
Okay. Determine the acceleration of B as a function of the acceleration of A, right?
You've got A up there.
They have what?
0.044
Oh, good.
meters per
Okay.
second. A sub A.
Okay, so we're looking for the acceleration of B as a function of the acceleration of A, and then we can plug in the given value there. Okay? Feel good? Well, this is velocity information. Let's examine that for just a second. The velocity of B, it looks like, is equal to negative half the velocity of A, doesn't it? Okay. So in other words, let's say I grabbed a hold of this body and I pulled it down at a certain speed. Body B coming down, well actually, maybe I should go over here and grab this guy since that's the way I wrote it. Let's say I grab this and I pull this body downward, body A downward at a certain speed. If I do that, then this body is going to be going which way? It will be a negative, won't it? Because notice my direction, my defined values here. Positive downward, positive downward. If you get positive answers, then that means you're in the correct direction. If you get a negative, it means it's really doing the opposite of that. So if I grab this body, pull it downward where I'm extending this, causing that term to be positive, then this result here is negative and half as much, which means this body is rising at half the speed that this body's going down. Make sense? This body's moving down at a certain speed, this is moving upward, contracting this distance as that body extends.